This lesson is a continuation of IB Physics topic 5.2, and what we're going to look at in this unit is basically resistors in series and parallel and the various concepts that are needed to be applied for resistors in series and parallel. In addition, we'll be looking at voltmeters and ammeters and the difference between ideal versions of these two tools and real version of these tools. So first off, I want to describe what an electric circuit is. Okay, an electric circuit must have an unbroken loop. Okay, the electrons must keep going around in a circle. If the circuit has a gap in it, the electrons can't flow, and so that does not constitute a circuit. Okay. The second thing a circuit must have is that it must have a battery or a power source to force the electrons to move around. Okay, in the picture, it shows the direction of conventional current flow. This is the flow of theoretical positive charges. We're aware that it's the electrons that flow, and the electrons flow out of the negative side of the battery or the short side of the battery and go in this all the way around the circuit back to the positive side. Okay, but we are going to be focusing completely on conventional current. Okay, so when we talk about current, it is always the flow of positive charges, which leave the positive side of the battery, goes around to the negative side of the battery. Okay, so we'll always be focusing on the conventional current unless the question specifically asks something about what direction do the electrons flow, or it's given as the electrons are flowing in this direction, something indicating non-conventional current flow. We'll also be running into a couple of additional electrical symbols. These symbols are also given in the data book. Okay, a cell and a battery are almost effectively the same thing. We'll talk about slight differences between them in topic 5.3. Okay, but electrically and mathematically they're going to be treated the same because we can place an arbitrary voltage pretty much for a cell or several cells put together to create a battery. Below the cell is a switch. Okay, the switch will usually be drawn open. Okay, but you have to think of it as closed. Or the switch will be open and closed depending on certain situations. So don't just treat it as an open circuit all the time. Voltmeters and ammeters are circles with the letter V and a little letter A as shown, and a lamp is basically kind of like a railroad crossing sign. Okay, again, all of these symbols are in your data book. If you need to look them up, please do so. Okay, electrical elements are primarily connected only in two ways. They're either connected in series, where one end is connected to the other end. Okay, the other two ends are connected to the rest of the circuit. Or it's in parallel. Okay, when it's in parallel, both ends of the electrical element are connected together. Okay, so in this case, this end is connected and this end is connected. Okay, so those are the two ways, either in series or in parallel. There is a third way, which is none of the above. None of the above happens when there's a branch point placed on a series connection, and that branch point goes somewhere else. Okay, and so that's none of the above. And that's actually a situation that we'll encounter in a lesson or two. So these are a couple of examples, and you need to decide which of these are in series, which of them are in parallel, or which of them are none of the above, neither series nor parallel. Okay. If you looked at them and are able to decide, either pause the video now and think about it, or continue watching. So this one is in series, okay? Although it's not in a straight line, they're only connected at one point, and the two ends connect to the rest of the circuit. Same with this one, okay? The upper right-hand corner is also in series. The two resistors look like they're in parallel, but this end is not connected to this end. So therefore, it is still in series. Okay, the bottom two, these are both parallel, okay? Because the end of this resistor is connected there, and the other end is connected here. Same here. Okay, so the point of this slide is to not get caught up in the picture geometry and focus on the electrical geometry. How many points of connection are there? If there's only one and no branch points, it's in series. If it's connected on both sides, then it's in parallel. Okay, a couple of concepts with resistors in series. Okay, the primary concept that you need to know for resistors in series is that the current through any set of resistors in series will be the same. This is a continuation of conservation of charge, because the electrons come in on one side and they must leave at the same rate on the other side. Okay, otherwise it's implying that electrons are building up somewhere. If that's true, then after a while you've basically built up an infinite number of electrons, and that just can't happen. Okay, so current through resistors in series must be the same. The voltage, however, will be different as long as my resistors are different. Okay, so we can frequently replace a set of resistors, R1 and R2, with a single resistor. Okay, just like we did when we were looking at systems. Okay, we grouped multiple objects together, and that grouped object helped us to solve problems by getting us additional information. In this case, we can do the same with resistors, okay? And the way to replace them is to simply add the two resistors together and replace that, okay, with R1 plus R2, okay? So here's the formula that we will be using for resistors in series, okay? And this will allow us, as long as we know the voltage drop across the whole thing, it allows us to calculate the current through the equivalent resistor, and the current through the equivalent resistor is the same as the current through the individual resistors, because that's the feature of resistors in series. For resistors in parallel, okay, again, all the current coming in leaves the resistors in parallel. However, it splits while it's in there, okay? And it splits based on choosing the path of least resistance, okay? So in this case, the voltage differential across them will be the same. And that's the primary concept you need to recall for resistors in parallel. The voltage will be the same. The current will be different across each one, okay? The total current, I1 plus I2, must equal the I shown in the diagram above. And we'll talk about that soon. Okay, so going through the calculation, we can find, again, an equivalent resistance for these two resistors, or set of resistors if it's more. And the equivalent resistance is that inverse formula we saw last year, where 1 over the equivalent resistor in parallel equals 1 over R1 plus 1 over R2 plus dot, dot, dot. Okay, this is probably the area where I see most of the math mistakes that are made. Okay, I'll frequently see students do like 1/3 plus 1/4 equals 1/7. Okay, that's just not how fractions work. Okay, so I would highly suggest while you're doing resistors in parallel to slow down and double check your math. The other mistake people make is thinking that the left side of this equation is simply R parallel, and forgetting to flip their fraction that they get afterwards. Okay. So, brief discussion about voltage dividers and current dividers. We didn't really discuss this last year, okay? But resistors in series are called voltage dividers. They're called that because that middle voltage, okay, the VB in this picture, okay, is a fraction of the voltage difference between VA and VC. Okay, it's basically just a proportion. Okay, it's based on the resistor in question and the total resistance. Okay, so this is a proportion of the total voltage here. Okay, resistors in parallel are called current dividers because they divide the current between them. This formula is a little more complicated because, and I wouldn't rarely recommend using this in situations with more than 2 resistors. Okay, it's a little different because the current through R1 is based on the fraction of R2. Okay, what I describe as counter proportional. Okay, and that's because it goes through the path of least resistance. Okay, so if I have 2 resistors, a 3 ohm and a 5 ohm, okay, the amount of current going through the 3 ohm resistor is 5/8 of the total current. Okay, so here's an example of a current voltage divider, okay? Voltage dividers are also called potential dividers, okay? And if I put 2 of them together, I end up with a potentiometer, okay? Remember, the potentiometer basically slides from left or right, changing the proportion of the resistors on each side, okay? And so the potentiometer basically acts as a voltage divider, okay? So why do we have these voltage dividers? Okay, voltage dividers are very useful for controlling electronic elements. Okay, because on the right side of these diagrams, I have an electronic switch that either turns on or turns off at a specific voltage. Okay, and when I get to that voltage, I can change the values of the resistors using light dependent or temperature dependent resistors. Okay, and thereby turn on or off lights or air conditioning or heating elements. Okay, so potential dividers are going to be very useful for us going forward. Okay, in terms of shortcuts, because of the complexity of doing least common denominator and adding fractions when you no longer have a calculator, most of the resistors combinations on the paper 1 will be integers and multiples of single values. Okay, so a couple of shortcuts I want you to use, especially on the paper 1. Okay, for resistors in parallel, the equivalent resistance will always be less than the smallest resistor. So if I have a 1 ohm resistor and a 100 ohm resistor in parallel, it'll still be less than 1. Okay, the bigger the other one is, the closer to 1 that it will be. Okay, so even if I have a 1, a 2, a 3, a 5, a 10, a 20, a 100, the equivalent resistance will still be less than 1. Okay, similarly, okay, if I have multiple parallel resistors of the same value, so R1 equals R2 equals R3, okay, then the equivalent resistance is simply the number of those resistors. In this diagram I have 2, so I just divide that R1 by 2 and I get my equivalent resistance that way. For instance, if I had 2 10 ohm resistors in parallel, the equivalent resistance would be 10 divided by 2, or just 5. If I had 3 of them, it becomes 10 divided by 3, or 3.3 ohms. Okay? So that brings us to voltmeters and ammeters. Okay? Voltmeters measure voltage differential. And because they voltage differential, they must go on either side of the resistor. Okay, or in other words, they go in parallel with what you are trying to measure. Okay, ideally the voltmeter will have an infinite resistance. Okay, because I want to impact the circuit as little as possible. I don't want any current going through my voltmeter. Okay, in actuality, I can't get infinite resistance, so in actuality, the voltmeter will have a large but finite resistance, usually somewhere around 100 kiloohms. Okay. Ammeters, however, measure current, okay, and so they go in series. They need to count every single electron that goes through, so they'll go in series. Ideally, the ammeter will have 0 resistance, and again, in actuality, because I can't get 0, in actuality, the ammeter will have a small resistance, usually in the unit ohms, okay, 3 ohms, 5 ohms. In both cases, if the voltmeter or ammeter actually has resistance, you need to include that resistor in your circuit analysis. Okay. Thank you.